Why does a magnitude 5.4 earthquake, the kind of small routine tremor that happens dozens of times a year along the Aleutian Arc, trip a tsunami warning system that almost never fires for events that small? That is the question I want you to hold in your head for the next 2 hours, because at 8:05 in the morning, Alaska time, on April 25th, 2026, that is exactly what happened. The system flagged a quake that, on paper, should have been background noise, and then it told an entire stretch of southern Alaska to brace. The reason is not in the seismic data, the reason is in the place. And what I'm about to walk you through is one of the strangest, deadliest, and most institutionally haunted corridors of seafloor on the planet. A corridor most Americans have never heard of, even though the United States government quietly considers it one of the most dangerous tsunami zones in the Pacific. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. A tsunami from America's most forgotten megathrust. At 8:05 and 56 seconds in the morning, Alaska time on April 25th, 2026, the seafloor about 90 kilometers south of Sandpoint twitched. It was not a violent twitch. It was not the kind of shudder that rattles dishes off shelves or sends people running into doorways. It was a magnitude 5.4 earthquake at a depth of around 35 kilometers, which in the language of seismology is the kind of event that gets logged, tagged, filed, and almost entirely ignored. The Aleutian Arc produces dozens of these every single year. They are background noise. They are the geological equivalent of a cough in a crowded room. And yet, less than 3 minutes later, the United States Tsunami Warning System did something that almost never happens for an earthquake of that size at that depth. It fired. An alert went out. Coastal communities along a stretch of southern Alaska were told, in the cold mechanical language of automated hazard messaging, that a tsunami was possible and that they should be prepared. 3 minutes. That is roughly the time it takes to boil water for tea. That is faster than most people can find their car keys. That is, in the world of geophysical decision-making, almost instantaneous. I want you to sit with the strangeness of that for a moment. Because here is the thing about magnitude 5.4 earthquakes. They happen all over the world all the time, and they almost never produce tsunamis. The general threshold that seismologists use, the rough cutoff above which a quake even starts to become a candidate for a serious ocean wave, sits somewhere around magnitude 6.5, and even then only if the rupture is shallow enough and the geometry is right. To trigger a basin-wide tsunami of the kind that crosses oceans, you typically need magnitude 7, 8, or higher. A 5.4 at 35 kilometers depth is, by every conventional measure, well below the threshold where any of this should happen. So why did the system fire? That is the question this entire video is going to answer, and I want to warn you up front, the answer is not a simple one. The answer involves an earthquake that happened 80 years ago, a lighthouse that was scraped off a cliff by a wave the size of a 14-story building, 159 dead in Hawaii, a disputed underwater landslide the size of a small mountain range, and a kind of earthquake that scientists still do not fully understand. The answer involves software written with the memory of a disaster baked into its code. The answer involves a stretch of seafloor that most Americans have never heard of, but that the United States government quietly considers one of the most dangerous tsunami corridors on the planet. Because here is what nobody told you in the headlines. The warning system did not fire because of the earthquake. It fired because of where the earthquake happened. And in this specific corridor of the Eastern Aleutian Arc, the rules that govern every other piece of subduction zone real estate on Earth seem to bend, twist, and occasionally break entirely. A small earthquake here is not the same as a small earthquake anywhere else. The history of this place has taught the warning system to assume the worst, even when the seismic numbers say otherwise. What you have to understand is that the alert went out before any ocean sensor confirmed anything, before any tide gauge spiked, before any deep ocean buoy registered a passing wave. The decision to warn was made on the basis of seismic data alone, processed through an algorithm that had clearly decided this particular set of coordinates deserved special treatment. That is not a bug. That is not an overreaction. That is, I am increasingly convinced, a feature. A piece of risk memory encoded in software, sitting quietly in a server room somewhere, waiting for a specific pattern at a specific place to trip a specific switch, and the switch tripped. I want you to think of the warning system for a moment as a kind of institutional ghost, a spirit haunted by old failures. The ghost remembers what happened the last time the ground moved at these coordinates. The ghost remembers the lighthouse. The ghost remembers high-low. The ghost was, in a very real sense, born out of those deaths. And when the seismometers chirped at 8:05 and 56 seconds on April 25th, the ghost did not wait for proof. It reached out and pulled the alarm because the cost of being wrong about staying silent in this corridor has historically been measured in bodies. There is a strange paradox at the heart of all hazard warning systems. When they work perfectly, nothing happens. There is no disaster. There is no death toll. There is no dramatic no death toll. There is no dramatic footage. There is just a brief moment of inconvenience, a few hours of disruption, and then life goes on. The system that prevented catastrophe looks, to the casual observer, exactly like a system that overreacted. A successful tsunami warning that does not result in a tsunami is functionally indistinguishable from a false alarm. The public understandably gets annoyed. The headlines treat it as a non-event, and the next time the system fires, just a little bit of trust has been eroded. But 3 minutes, in the context of what could happen here, is the difference between a warning and a memorial. 3 minutes is the gap between getting people off the beach and counting how many never made it back. The 1946 earthquake, which I am going to spend a lot of time on later in this video, produced a tsunami that hit Scotch Cap Lighthouse within roughly 5 minutes of the rupture. 5 minutes. The keepers of that lighthouse did not have 3 minutes of warning. They had no warning at all. And the wave erased them, and the lighthouse, and any meaningful trace that either had ever existed. So when I tell you that the system fired in 3 minutes for a magnitude 5.4, I want you to hear the echo in that number. I want you to hear what the algorithm was hearing. Because to understand why a small earthquake triggered a big response, you have to understand the place where that earthquake happened. And to understand the place, you have to go back, way back, to a morning in April 1946 when an entire coastline learned, in the most brutal way possible, that the size of an earthquake is not always a reliable indicator of what comes next. Stay with me. Because what we are about to walk into is not just a story about one small quake on one quiet morning in Alaska. It is a story about the limits of what we can measure, the things our instruments cannot see, and a corridor of the Pacific seafloor that has been quietly rewriting the rules of tsunami science for the better part of a century. And the warning that fired today might not be the last one we hear from it. 3 minutes. That is all the system needed. The question is, what did it know that we are still trying to figure out? The corridor in question stretches along the eastern end of the Aleutian Arc, that long curving chain of islands and underwater mountains that arcs from the Alaska Peninsula out toward Russia like a stone skipped across the top of the Pacific. This is where the Pacific Plate, one of the largest tectonic plates on Earth, dives beneath the North American plate at a rate of roughly 6 to 7 centimeters per year. That might not sound like much. It is about the speed at which your fingernails grow. But over geological time, that constant grinding convergence builds up enormous stresses in the rock. And when those stresses release, they release in ways that can rearrange coastlines. The Aleutian megathrust is what we call this kind of fault. A megathrust is a subduction zone interface, where one plate slides beneath another, and they are responsible for the largest earthquakes ever recorded on this planet. The 1960 Chile event, the 2004 Sumatra event, the 2011 Tohoku event, all of these were megathrust earthquakes. They are quite simply the most dangerous geological features on Earth, and the Aleutian megathrust is one of the longest in the world, running for thousands of kilometers along the southern edge of Alaska and out into the open ocean. But here is what people do not generally appreciate about this particular megathrust. It is not uniform. It does not behave the same way along its entire length. Different segments of the fault have different geometries, different histories, different personalities, you might say. Some sections rupture frequently in moderate events. Some sections lock up tight and accumulate stress for centuries before releasing it all in one cataclysmic slip. And some sections, the strange ones, the ones that keep seismologists awake at night, behave in ways that do not fit any of the standard models. The eastern segment, the corridor near Unimak Island where today's earthquake occurred, falls into that third category. It is a problem child. It is the part of the fault that does things you cannot predict from theory alone, and the reason has to do with what is sitting on top of it. When you have a subduction zone, you also tend to have what is called an accretionary prism. As the descending plate scrapes its way under the overriding plate, it shaves off layers of marine sediment, deep ocean mud, and chunks of crustal rock, piling them up like the curl of dirt that builds in front of a bulldozer blade. Over millions of years, this prism can grow into an enormous wedge of weakly consolidated, water-saturated material draped along the upper edge of the subduction interface. It is loose, it is slumpy, it holds water like a sponge, and it sits often on a slope that is steeper than it looks. The Eastern Aleutian Corridor has one of the thickest, most sediment-rich accretionary prisms anywhere along the megathrust. Glacial meltwater from Alaska has been dumping ground-up rock into the Bering Sea and the North Pacific for tens of thousands of years. Marine biological productivity adds its own slow rain of organic material to the seafloor. Underwater currents redistribute it. The result, over geological time, is an enormous pile of unstable material balanced on a fault that periodically shudders. You can probably already see where this is going. This is why I keep coming back to that 3-minute alert. Because in most subduction zones, the relationship between earthquake size and tsunami size is reasonably predictable. Big quake, big wave. Small quake, no wave. But in the Eastern Aleutian Corridor, that relationship breaks down. Here, you can have a moderate earthquake that produces an enormous tsunami, because the earthquake is not the only thing displacing water. The earthquake might trigger a submarine landslide, and the landslide might shove a volume of seafloor sideways or downward in a way that dwarfs the displacement from the rupture itself. The wave that rolls out across the ocean is not the wave the earthquake should have made, it is the wave the landslide made, and the seismometers, listening for the earthquake, often have no idea the landslide ever happened. This is what I mean when I say the corridor breaks the rules. We have a phrase in hazard science for fault segments like this. We call them tsunami efficient. It sounds clinical, but what it really means is that this stretch of fault, for reasons we still do not fully understand, is unusually good at turning earthquake energy into ocean waves. Some segments of subduction zones are tsunami inefficient. They produce big shaking but modest waves because the rupture happens deep, or because the geometry directs energy in unhelpful directions. The Eastern Aleutians are the opposite. They are tsunami efficient in the most dangerous possible way. Less shaking, more wave. You can compare this to other places along the Pacific Rim, and the contrast becomes obvious. In Japan, the relationship between seismic magnitude and tsunami amplitude has been studied for centuries, and it generally tracks. In Chile, you can predict, within reasonable error bars, what kind of wave a given rupture will produce. But in the Eastern Aleutian Arc, you have a long history of mismatches. Quakes that should have produced modest waves have instead produced monsters, and the geological reason has everything to do with that thick, water-soaked, gravitationally unstable sediment pile sitting on top of the fault. This is also a region where the slab geometry matters enormously. The angle at which the Pacific Plate descends beneath North America in this part of the Aleutians is shallow, somewhere around 10 degrees. A shallow slab means a wider zone of contact between the two plates near the surface. A wider near-surface contact zone means that when slip happens, it can extend up into the very shallow part of the fault. Where the rock is weakest, the sediment is thickest, and the displacement of the seafloor is greatest. It is a recipe for big tsunamis from earthquakes that, in any other setting, would barely register as ocean events. I want you to hold that idea in your head, because it is the key to everything that follows. Low shaking, high displacement potential. The shaking does not match the wave. The earthquake does not match the disaster. This is the signature of a place where conventional seismology can fail you, and it is the reason I am increasingly convinced that the warning system in 2026 did not wait for confirmation. It saw the coordinates. It pulled the trigger. Because in this specific, narrow, sediment-buried, slope-steepened corner of the Pacific, even a small earthquake is a question, and the answer to that question has, historically, been measured in lives. So what does that mean for how the warning actually got generated? How does an algorithm decide in the span of less than 3 minutes that a magnitude 5.4 deserves an alert when the same magnitude, 2,000 kilometers away, would be ignored entirely? That is the question I want to walk into next, because the inner workings of the United States tsunami warning system are, in some ways, more interesting than the earthquake itself. Here is how a tsunami warning system works, in broad strokes. When an earthquake happens, seismic waves spread outward from the rupture in all directions, travelling through the rock at speeds of several kilometers per second. Networks of seismometers around the world pick up these waves, and within seconds, automated algorithms start estimating three crucial parameters. Where did the earthquake happen? How big was it? How deep was it? The location, the magnitude, the depth. These three numbers are the foundation of the entire decision-making process. Once those parameters are estimated, the system runs them through a series of decision thresholds. If the magnitude is below a certain value, no alert. If the depth is greater than a certain value, no alert. If the location is on land rather than under or near the ocean, no alert. These thresholds exist because the vast majority of earthquakes do not produce tsunamis, and the system has to filter out the noise. You cannot send out a warning every time the ground moves. Public trust would collapse within weeks. But here is where it gets interesting. The thresholds are not the same everywhere. They cannot be the same everywhere, because different regions of the ocean have different tsunami histories, different geometries, and different known hazards. The decision rules for a quake in the Central Pacific are not identical to the decision rules for a quake in the Eastern Aleutians. The system has been tuned segment by segment over decades to account for what we know about each piece of fault, and the Eastern Aleutian corridor has a lower threshold for alerting than most other places because the historical record demands it. I want to be careful here, because the exact details of how these algorithms make their decisions are not always fully public, and I do not want to claim more certainty than I actually have. But based on what is known about how the National Tsunami Warning Center operates, and based on the published literature on regional tsunami hazard assessment, there are a few things that almost certainly contribute to a decision like the one made in 2026. The system likely looks at the duration of the rupture, not just the peak amplitude. It likely looks at the long-period component of the seismic signal, because slow earthquakes have more energy at long periods. It likely looks at the focal mechanism, the geometry of how the fault slipped, because a thrust event at the megathrust interface is a much bigger tsunami threat than a strike-slip event in the overriding plate. And it almost certainly applies a regional adjustment, a kind of asterisk attached to certain coordinates that says, in essence, in this place, even a small signal might mean a big problem. Be cautious. The regional adjustment is, in software terms, a piece of institutional memory. It is the system remembering that this corridor produced the 1946 event and the 1957 event, and that paleo-tsunami evidence suggests other events have happened here in the deep past that we do not have written records of. The algorithm carries that memory. It does not have to be told what 1946 was. The shape of 1946 is sitting in its decision tree, weighting the outcome. This is what I mean when I call it algorithmic bias from historical disasters. And I do not mean bias in the negative sense. I mean it in the engineering sense. The system has been deliberately tilted toward caution in places where caution has been historically justified. This is good design. This is what you want. The alternative, a system that treats every fault segment identically regardless of its track record, would be a system that sometimes underwarned places that desperately needed warnings. There is, of course, a trade-off. Every false alarm chips away at public credibility. Every alert that resolves with no observable wave gives some fraction of the population a reason to dismiss the next alert. The tsunami warning community knows this. They live with it. They have decided deliberately and with full awareness of the cost that the consequence of missing a real event in this corridor is so much worse than the consequence of issuing a precautionary alert that the math is not even close. And the math really is not close. Because here is the other piece of the puzzle. Ocean sensors, the things that can definitively confirm whether a tsunami is propagating across the open Pacific, take time. Coastal tide gauges have to wait for the wave to actually reach them, which can mean tens of minutes for a near-field event and hours for a far-field one. Deep ocean buoys, the famous DART system, can detect a passing wave faster, but they still need a few minutes of clean data to distinguish a real tsunami signal from background ocean noise. By the time the buoys give you a definitive answer, the wave is already on its way to somewhere, and if that somewhere is close to the source, the people there are already in trouble, so the warning has to go out before confirmation. There is no other choice. The system is designed to act on inference, not evidence. It looks at the seismic signal and asks, given everything we know about this place, what is the probability that something dangerous is happening? If that probability crosses a threshold, the alert fires. The wave might never come. Most of the time, the wave will not come, but the alert has to fire anyway, because the cost of waiting for proof is paid in human lives. This is the precautionary principle in its purest form. It is the philosophical foundation of every modern hazard warning system in the world, and it traces its roots, in the Pacific, directly back to the failure to warn in 1946. The system that fired in 2026 is, in a very real sense, the institutional descendant of that failure. Every line of code, every threshold value, every regional adjustment exists because at some point in the past, somebody died who did not have to. And in this case, the system fired and the wave did not come. The tide gauges stayed quiet. The buoys recorded nothing unusual. Within a few hours, the alert was downgraded and life along the southern Alaskan coast returned to normal. To the casual observer, this looks like a non-event, a blip, a footnote, the kind of thing that gets a 30-second mention on the evening news and then disappears into the noise. But to me, watching this from the outside, this was not a non-event at all. This was the system performing exactly as designed, in a corridor where the history demands it, on a fault segment that has a known capacity to produce disaster from inputs that look modest. The fact that no tsunami arrived does not mean there was no risk. It means the system absorbed the uncertainty on our behalf, made the cautious choice, and then let the ocean tell us in its own time whether the caution was needed. There is a phrase I keep coming back to here. Absence of evidence is not evidence of absence. The fact that nothing happened in 2026 does not retroactively prove that nothing could have happened. The corridor remains the corridor. The sediment remains unstable. The slab remains shallow. The fault remains capable of doing in the future what it has done in the past. And what it has done in the past is so far outside the bounds of what its earthquakes look like on paper that we are still, 80 years later, trying to figure out exactly how it did it. To understand that, we have to leave the present. We have to go back to a morning in April that almost no one alive today remembers and look at what happens when the same patch of seafloor does not get a warning system to protect it. Because before there was a Pacific Tsunami Warning Center, before there were dart buoys, before there were algorithms with regional adjustments, there was just a cold, grey ocean off the coast of Alaska, a lighthouse on a cliff, and a seismograph somewhere far away that registered an earthquake that did not at first seem particularly alarming. And then the wave came, and nothing about the way Americans thought about ocean hazards was ever the same again. Part 2. The earthquake that did not look dangerous. It was about 2 in the morning local time on April 1st, 1946, when the seafloor south of Unimak Island ruptured. The date is worth pausing on, April 1st. In some parts of the Pacific, the events that followed would later be misremembered as some kind of cruel cosmic joke, the ocean choosing the day of pranks to commit a mass murder. But of course the timing was meaningless. The fault did not check the calendar. It moved when it was ready to move, and when it moved it did so in a way that should have been impossible. The earthquake was, by the seismic instruments of the time, classified as roughly magnitude 7.4. That is a respectable earthquake. That is the kind of earthquake that, in a populated area, can knock down buildings and kill people directly through shaking. But it is not on its own the kind of earthquake that produces a wave capable of crossing 4,000 kilometers of open ocean and slaughtering people in another country. Magnitude 7.4 is a serious event, but it is not a basin-scale catastrophe, not by the standard rules. What modern seismologists, working with refined techniques and a much better understanding of long-period seismic waves, have since determined is that the original magnitude estimate was wrong. The actual moment magnitude of the 1946 earthquake was closer to 8.6. That is not a small correction. The difference between magnitude 7.4 and magnitude 8.6 is roughly a factor of 60 in terms of the actual energy released. The earthquake that the instruments of the day caught was a shadow of the earthquake that actually happened. Why did the instruments miss it? This is one of the most important questions in 20th century seismology, and the answer goes to the very heart of why that 2026 warning fired. The seismographs of 1946 were tuned to detect short-period seismic waves, the kind of high-frequency shaking that radiates from a typical earthquake rupture. They were not well equipped to detect long-period waves, the slow, rolling oscillations that come from a rupture that lasts longer and propagates more slowly than a normal quake. And the 1946 event, as we now understand it, was exactly that kind of slow rupture. It was an earthquake that took its time. It moved gradually, almost gently, along a long stretch of fault, displacing enormous volumes of rock without producing the violent high-frequency shaking that the instruments were watching for. The result was that on the morning of April 1st, 1946, the seismologists who looked at the records concluded that something significant had happened off the coast of Alaska, but nothing alarming. No widespread destruction was reported from Unimak Island or the Alaska Peninsula. The shaking, where it was felt at all, was described as moderate. There was no sense of imminent catastrophe. There was no panic. There was no warning system to fire because no warning system existed, but even if one had existed, it would have looked at the seismic data and seen no particular reason to sound an alarm. The earthquake did not look dangerous. The earthquake looked manageable. This is what I mean when I keep returning to that 2026 alert. Because the algorithm in 2026 knew, in a way that the human seismologists of 1946 could not have known, that the appearance of a quake in this corridor cannot be trusted, that the visible shaking is not the whole story, that the rules of normal earthquake interpretation simply do not apply at these coordinates. The institutional memory that fires a warning for a magnitude 5.4 today is, fundamentally, the lesson learned the hard way on April 1st, 1946, when the earthquake did not look dangerous, and the wave that followed it killed and killed and kept on killing. The location of the rupture is worth dwelling on. The epicenter sat off the southern coast of Unimak Island, in roughly the same corridor that produced the 2026 event. Not the same exact spot, but the same fault segment, the same accretionary prism, the same shallow slab, the same sediment-burdened, gravitationally precarious stretch of seafloor. When the warning system fired in 2026, it was effectively responding to a quake on the same chunk of Earth that had produced the 1946 disaster. 80 years apart, same neighbourhood, same fault. And in 2026, the system had the benefit of knowing what 1946 had taught it. What the seismologists of the time did not yet understand was that the relationship between earthquake size and tsunami size in this part of the world was broken. They were working with a model of subduction zone behaviour that assumed, reasonably enough, that bigger ruptures meant bigger waves and smaller ruptures meant smaller waves. That model held up in most parts of the Pacific. But the Eastern Aleutian corridor was, even then, an exception that nobody fully appreciated. The combination of slow rupture, shallow geometry, thick sediment, and probable submarine slope failure conspired to produce a wave that was wildly disproportionate to the seismic signal. The earthquake said one thing, the ocean said another, and nobody was listening to the ocean because the ocean had not yet started to speak. There is a haunting quality to this part of the story because for a few minutes after the rupture, in the cold pre-dawn darkness over the North Pacific, nothing was wrong yet. The earthquake had happened. The seafloor had moved. Somewhere, deep beneath the surface, an enormous volume of water had been displaced. But the wave that this displacement created had not yet reached anyone. It was travelling outward, in expanding rings, at the speed of a commercial jet, and the shore it was about to hit first was a thin, exposed strip of rock at the southwestern tip of Unimak Island, where 5 men were standing watch in a lighthouse that they believed to be unsinkable. The lighthouse was called Scotch Cap. It had been built to withstand the full fury of the North Pacific, and it had done so for decades. It was a reinforced concrete structure, multiple stories tall, anchored into the bedrock of the island, perched on a cliff above the sea. It was the kind of building that a person standing inside it might reasonably believe could not be moved by water. Storms came and went. Waves crashed against the cliffs and retreated. The lighthouse remained. It was a constant in a region of constants and changes, the steady eye that watched over one of the most remote and treacherous shipping passages on Earth. And then, sometime around 5 minutes after the earthquake began, the wave arrived. The run-up at Scotch Cap, the height to which the water rose above sea level, has been measured at approximately 42 metres. Let me say that again, because it does not become any less staggering with repetition. 42 metres. That is a wall of water roughly 138 feet tall. That is taller than a 14-storey building. That is taller than the Statue of Liberty from foot to torch. That is a volume of water moving at speed that, when it makes contact with anything in its path, transfers an amount of kinetic energy that the human mind genuinely struggles to comprehend. Concrete is not a meaningful obstacle to a wave like that. Steel rebar is not a meaningful obstacle. The lighthouse, the entire reinforced concrete lighthouse, with its cast iron lantern and its decades of accumulated paint and equipment and human history was simply removed, scraped off the cliff, erased. The 5 men on duty did not survive. They could not have survived. The wave came and went so quickly that there was no time to do anything. There was no warning. There was no siren. There was no chance to climb to higher ground because the wave was higher than any ground the lighthouse keepers could have reached in the seconds available to them. They were there, and then they were not. And the cliff where their station had stood was bare, swept clean of everything but the foundation. When rescuers eventually reached the site, they found scattered debris, some pieces of equipment, and almost no recognisable trace of the structure that had stood watch over that corner of the Pacific. This is the disaster the warning system in 2026 remembers. This is the event encoded in the algorithm. When the seismometers chirped at 8:05 and 56 seconds on April 25th, 2026, the system was, in a very precise sense, reaching out across 80 years to try to make sure that nothing like Scotchcap would happen again. The 3-minute alert was, fundamentally, a reaction to the absence of a warning 80 years earlier. But the wave did not stop at Scotchcap, it kept going. And here is where the story becomes something other than a regional tragedy. Here is where the story becomes a Pacific Basin event, and where the people of an island chain 4,000 kilometers away begin to learn, with no warning whatsoever, what was about to happen to them. The wave radiated outward from the source in expanding circles, travelling across the deep ocean at roughly the speed of a passenger jet aircraft. In the open Pacific, a tsunami like this is almost invisible at the surface. The wave height in deep water might be only a metre or two, spread over a wavelength of hundreds of kilometres. A ship sailing through it would feel nothing at all. The ocean would not look angry. The ocean would not look unusual. But beneath that calm surface, an enormous volume of water was in motion, propagating across the basin with a kind of patient inevitability, heading towards shorelines where, in just a few hours, it would slow down, pile up, and become catastrophic. 4 hours and 34 minutes after the rupture in Alaska, the leading edge of the wave reached the Hawaiian Islands. The town of Hilo, on the eastern coast of the Big Island, sits inside a wide bay that is geometrically tuned, almost as if by malicious design, to amplify incoming waves from the north. Hilo Bay has been called a tsunami trap by the people who study these things, because its shape funnels and concentrates wave energy in ways that other coastlines do not. When a Pacific Basin tsunami arrives at Hilo, the bay does not dissipate it. The bay focuses it. On the morning of April 1st, 1946, no warning system existed to tell the people of Hilo what was coming. There was no Pacific Tsunami Warning Center. There were no sirens. There were no evacuation maps. The earthquake in Alaska had not been felt in Hawaii at all, because the seismic waves had radiated outward and passed Hawaii hours before the tsunami did, and the ground in Hilo had stayed completely still. To the people of Hilo in the early morning hours of that day, nothing was wrong. The ocean was the ocean. Life was beginning. Boats were heading out. School children were getting ready for the day. And then the water did something strange. It pulled back. The harbour began to drain, as if some enormous plug had been pulled somewhere out beyond the horizon. Boats grounded on mud flats that had not been visible in living memory. Fish flopped in the suddenly exposed sand. People came down to the waterline to look, because they had never seen anything like it, and they did not understand what was happening, because nothing in their experience had prepared them to recognise the warning. The drawback of water from a coastline is one of the most reliable natural signs of an incoming tsunami. The wave has a trough as well as a crest, and depending on which arrives first, the ocean can either suddenly rise or suddenly fall. A falling ocean is the trough leading the way. The crest, the actual wall of water, is following behind it, and when it arrives fast. The first major wave hit Hilo with a run-up of approximately 10 metres in places, less in others, but everywhere it hit it was enough to overwhelm the waterfront. The wave swept inland, picking up boats, cars, buildings and people, and carried them as a churning mass of debris into the heart of the town. The water peaked, paused, and then began to drain back out, dragging everything that was not anchored down with it back into the bay. And then, in a pattern that is typical of basin-scale tsunamis, more waves came. Multiple wave trains, separated by minutes, each one different from the last, some larger, some smaller, but all of them deadly. By the time the ocean finally settled and the people of Hilo began to count, at least 159 of their neighbours were dead. Some had been crushed by debris, some had drowned, some had simply been swept out to sea and were never recovered. Many of the dead were children, because schools along the waterfront had been forming up for the day when the wave hit, and the children had been gathered in places that the water reached. The town itself was devastated. Buildings had been ripped from their foundations and turned to splinters. Boats had been carried hundreds of metres inland and deposited on streets. The waterfront, which had been the economic and social heart of the community, was simply gone, and nobody had warned them. There had been no system, there had been no algorithm, there had been no 3-minute alert. There had been only the strange, silent drawing back of the water, and the few minutes between the drawback and the arrival of the wave, which was not enough time for most people to even understand what was happening, let alone get to safety. The ratio of the earthquake to the disaster, when you lay it out side by side, is what makes 1946 such a defining event in the history of geophysics. The seismic instruments of the day registered a magnitude 7.4. Modern reanalysis says it was closer to 8.6. The shaking, where it was felt at all, was moderate. The tsunami, by contrast, had a tsunami magnitude, the so-called MT scale, of approximately 9.3. That is the scale that measures the size of the wave rather than the size of the earthquake, and it is the scale that, in this part of the Pacific, increasingly seems to be the only one that matters. The wave was so far outside the bounds of what the earthquake should have produced that, for decades afterward, scientists struggled to explain it. The simple model, in which seismic moment release directly translates to seafloor displacement, and seafloor displacement directly translates to wave height, simply did not work for 1946. The numbers did not balance. There was a missing term in the equation. The earthquake was too small to have made a wave that big. This is the missing mechanism that the corridor in 2026 is still hiding from us, and it's the reason why a magnitude 5.4 can fire a warning system in 3 minutes. Because if a magnitude 8.6 can produce a tsunami magnitude 9.3 through some combination of slow rupture and submarine slope failure, then nobody can be entirely sure where the lower bound is. Nobody can be entirely sure how small an earthquake has to be in this corridor before the rules apply normally. The system in 2026 was not willing to find out. What was the missing mechanism? The leading hypothesis, developed and refined over the past 2 decades by researchers, including Gerard Fryer, Hermann Fritz, Emile Ocal, Roland von Huene, and others, is that the 1946 tsunami was not produced primarily by the earthquake itself. It was produced by an enormous submarine landslide that the earthquake triggered. A volume of seafloor sediment, possibly as much as 200 cubic kilometres, slid down the continental slope south of Unimak Island, and the displacement of water caused by that slide is what generated the catastrophic wave. 200 cubic kilometres. That is a volume of material roughly equivalent to the entire above-water portion of Mount Fuji. Imagine that volume of mud and rock and sediment sitting precariously on the slope above the deep Pacific, suddenly being released by the shaking of the earthquake. Imagine it accelerating downhill, accelerating through the water, displacing the ocean above it as it went. The wave that resulted was not the wave the earthquake should have made, it was the wave the landslide made. And the landslide was invisible to the seismometers, because seismometers are designed to detect rapid rock motion, not slow sediment failure. There is some scientific debate about the details. The landslide hypothesis has not been universally accepted, and some researchers argue that the volume estimates are too large, or that the rupture itself can account for more of the wave than the landslide model implies. The seafloor mapping of the area, which would ideally show a single clean scar where 200 cubic kilometres of material had detached, has not produced a definitive smoking gun. Some researchers have suggested that the failure may have happened in multiple stages, or as a series of distributed slumps rather than one catastrophic slide, which would make the geological record harder to read. But the core insight stands. Whatever exactly happened on the seafloor in 1946, the wave was bigger than the earthquake should have made it. Some additional mechanism was at work, and the most plausible candidate, given the geology of the region, is mass movement of sediment, slope failure, a landslide, or a family of landslides that turned a moderate earthquake into a Pacific Basin disaster. This is what the corridor in 2026 is still capable of. This is what the warning algorithm in its silicon way was reacting to when it fired the alert. Because if the mechanism that drove the 1946 wave was sediment failure rather than fault rupture, then the size of the earthquake is not, on its own, a reliable predictor of the size of the wave. The shaking can be modest. The displacement can still be enormous. The thing the seismometers measure is not the thing that matters, and the only sensible response, in the face of that uncertainty, is to warn first and ask questions later. Part 3. The birth of a bias. The aftermath of the 1946 disaster reshaped American thinking about ocean hazards in a way that almost no other natural event has. The deaths in Hilo were not just a tragedy, they were a moral indictment. A wave had killed 159 people in an American territory, 4 hours and 34 minutes after an earthquake that had been recorded by seismographs across the country. There had been time to warn them. There had been infrastructure that, with the right design, could have transmitted a warning. There had been, in principle, every opportunity to save those lives, and nobody had. Because nobody had built the system that would have done it. Within a few years, that began to change. The United States Coast and Geodetic Survey, which had responsibility for monitoring earthquakes and ocean conditions, began work on what would eventually become the Pacific Tsunami Warning Center, established in 1949 in Hawaii. The mandate was simple in concept and is enormously difficult in execution. Detect the earthquakes that might produce tsunamis, estimate as quickly as possible whether a wave was likely, warn the populations along the Pacific coast in time for them to act. The model assumed that there would be hours, in most cases, between the rupture and the arrival of a far-field wave. The 4-hour travel time from Alaska to Hawaii in 1946 suggested that there was a window in which lives could be saved, if only a system existed to use that window. The system grew. Over the following decades, it acquired more seismometers, more tide gauges, more sophisticated communications. It learned from each subsequent event. The 1960 Chile earthquake, which produced a tsunami that killed people across the entire Pacific basin, including in Hawaii and Japan, demonstrated both the power of the new warning system and its remaining limitations. The 1964 Alaska earthquake, the second largest ever recorded, produced waves that hit California and Oregon and reaffirmed the need for a warning network. The 1965 Aleutian earthquake, the 1975 Hawaii event, the 2004 Indian Ocean catastrophe that killed more than 200,000 people in countries that had no warning system at all, each event added another layer of urgency, another lesson, another piece of code. The philosophy that emerged from all of this is what hazard scientists sometimes call the precautionary doctrine. When in doubt, warn. When the data is ambiguous, warn. When the cost of a false alarm is much smaller than the cost of a missed event, warn. The system was deliberately tilted toward overwarning because the alternative was too horrible to contemplate. The institutional memory of Hilo, of Scotch Cap, of the missing window in 1946 was baked into every threshold and every decision rule. And this is the philosophy that fired the alert in 2026. The system did not need to be certain that a tsunami was coming. The system needed only to be uncertain enough that the precautionary doctrine kicked in. A magnitude 5.4 in the eastern Aleutian corridor cleared that bar, where a magnitude 5.4 anywhere else in the world would not have, because the system remembered, because the algorithm carried the ghosts of Hilo with it, because 3 minutes was and is the kind of margin that the dead of 1946 did not have. There is something almost poetic about it, if you can step back from the human cost long enough to see it. A century ago, an entire town learned the hard way that the ocean could kill them in their sleep. From that lesson, a system was built, and the system grew, and the system passed through generations of engineers and scientists and policymakers, and along the way it acquired memories of its own. By the time 2026 rolled around, the system did not need any human being to tell it what 1946 had been. The shape of 1946 was already inside it. It was watching the same fault, with the same patience, ready to act before the Earth had even finished moving. And that brings us to the deeper question. What exactly is the system afraid of? What is the mechanism hidden somewhere beneath the surface of the eastern Aleutian Arc that turns small earthquakes into ocean disasters? Because the answer to that question is not yet fully known. The science is incomplete. The corridor still holds secrets that the best instruments in the world have not been able to fully extract. And until we understand what is happening down there, the warning system will keep firing in 3 minutes or less every time the ground twitches in this place, because the alternative is unthinkable. Part 4. Tsunami earthquakes and the quiet catastrophe. There is a category of earthquake that scientists have learned, slowly and at considerable cost, to fear in a special way. They are called tsunami earthquakes, and the name is misleading. It does not mean any earthquake that produces a tsunami. It means a specific kind of earthquake whose tsunami is wildly disproportionate to its shaking. A tsunami earthquake is, by definition, an event where the ocean wave is much, much bigger than what you would predict from the felt or measured ground motion. It is the technical term for the exact phenomenon that the Eastern Aleutian corridor seems specialized in producing. The first time the scientific community really paid attention to this category was after the 1896 Sanriku event in Japan. A modest earthquake by the standards of the Japan Trench, with shaking that residents described as gentle, produced a wave that killed more than 22,000 people along the northeastern coast of Honshu. The ratio of the wave to the quake was so absurd that it took decades for seismologists to develop a framework that explained it. The framework, when it finally emerged, centered on the idea that some earthquakes rupture very slowly, propagating along the fault at unusual speeds, and produce most of their energy in long-period seismic waves that traditional instruments are not optimized to detect. A tsunami earthquake, in modern terms, is one that ruptures in the shallowest part of the subduction zone, where the rock is weakest and the sediment is thickest. The rupture takes longer than a normal earthquake of similar moment magnitude. The slip propagates at a slower velocity. The high-frequency seismic radiation, the part that makes buildings shake, is deficient relative to what the moment magnitude would predict. But the seafloor displacement, the actual physical movement of the ground beneath the ocean, is unusually large for the seismic signal. The water above this displacement gets shoved upward or downward by an amount that is much greater than the high-frequency shaking would suggest, and a much larger tsunami results. This is the model that, when applied to the 1946 event, helps to explain why the original magnitude estimate was so low. The earthquake did not radiate the high-frequency energy that the seismographs were watching for, because much of the rupture happened in the slow, soft, sediment-loaded shallow part of the fault. The slip was real. The slip was enormous. But it was happening in a regime where the standard relationship between shaking and slip simply broke down. The seismic instruments saw a magnitude 7.4. The seafloor did something much, much bigger than that. What makes tsunami earthquakes especially dangerous is that, by the very nature of their physics, they tend not to feel dangerous to people on land. Coastal residents who experience a normal magnitude 8 earthquake know they have just experienced a major event. The shaking is violent. The ground rolls. Buildings sway, sometimes collapse. People run outside. The earthquake announces itself as an emergency. But a tsunami earthquake does not announce itself the same way. The shaking, even for a very large rupture, can feel modest, unremarkable, the kind of thing that you might notice and shrug off. There is no obvious cue to start running for higher ground. There is no body-level alarm. The body, which evolved to interpret violent shaking as a signal of mortal danger, gets a signal that is too quiet to take seriously, and then the wave comes anyway. This is what makes tsunami earthquakes uniquely lethal. They violate the intuition that the size of the shaking predicts the size of the threat. They produce disasters in populations that, by the evidence of their senses, had no reason to believe a disaster was about to happen. This is exactly the regime in which the Eastern Aleutian corridor seems to operate. The accretionary prism, the thick wedge of poorly consolidated sediment piled along the upper edge of the megathrust, is the perfect substrate for slow rupture. The water-saturated material reduces frictional coupling. The shallow slab geometry means that ruptures can extend all the way up to the seafloor, without encountering the kind of strong, dry rock that would generate high-frequency shaking. The conditions are tailor-made for the production of tsunami earthquakes, and the historical record suggests that the corridor has produced at least one, and possibly multiple events that fit this pattern. I want you to pause and notice how much this changes the meaning of the 2026 alert. If the corridor is capable of producing tsunami earthquakes, events whose seismic signal underestimates their true displacement, then a magnitude 5.4 reading from this region is not necessarily a magnitude 5.4 event. It is a magnitude 5.4 reading. The actual rupture might be larger, the actual seafloor displacement might be greater than the magnitude suggests. The warning system, faced with this possibility, has to consider that the number on its screen is potentially a lower bound rather than a true measurement. And in the Eastern Aleutians, that consideration has become the default. The challenge of detecting tsunami earthquakes in real time is one of the central unsolved problems of operational seismology. Researchers have developed techniques that look at the long-period component of the seismic spectrum, comparing it to the high-frequency component, to identify events with anomalous slip durations. There are techniques that track the apparent rupture velocity. There are techniques that look at the focal mechanism and the depth of the rupture. None of these techniques is perfect. All of them require data that takes time to acquire and analyze, and all of them are operating under the constraint that the warning, if it is going to be useful, has to go out within minutes of the rupture before the analysis is fully complete. This is why the precautionary doctrine matters so much in this corridor. The system cannot wait to be sure it is dealing with a tsunami earthquake before it warns. By the time the analysis is complete, the wave, if there is one, may already be hitting the coastline. The decision has to be made on partial information, in conditions of fundamental uncertainty, with the knowledge that the cost of being wrong is measured in lives. And yet, even with all of this, tsunami earthquakes are only one piece of the puzzle. They explain part of why the Eastern Aleutian corridor is so dangerous. They do not explain all of it, because the other piece of the puzzle is the part that does not even need an earthquake to be tsunami earthquake-sized. The other piece is what happens when the shaking, however small, hits a slope that was already on the edge of failing. Part 5. Landslides as force multipliers. I want you to imagine, for a moment, a pile of wet sand on a beach. You have built it up steeply, more steeply than it would naturally settle. It is balanced. It is just barely holding its shape. And then you give the sand a little tap. Not a big shove, just a tap. And the whole pile slumps, all at once, releasing the energy you put into it plus an enormous amount of energy that was already stored in the unstable geometry. The collapse is much bigger than the trigger. The wet sand pile is a force multiplier. The continental slope south of Unimak Island is, on a vastly larger scale, exactly this kind of system. The thick accretionary prism that has been accumulating along the Eastern Aleutian Arc for millions of years sits at angles that, in places, exceed the natural angle of repose for the materials involved. The sediment is water-saturated. The pore pressures within the sediment, the pressure of the water trapped between the grains, can be unusually high in certain layers, reducing the effective friction that holds the slope together. The whole system is a precariously balanced mass of unstable material, held in place largely by the absence of a sufficient trigger. When an earthquake happens nearby, even a relatively modest earthquake, it can provide that trigger. The shaking does not have to be strong enough to cause catastrophic damage on land. It just has to be strong enough to nudge the slope past its tipping point. Once the slope starts to fail, the failure can propagate with one slumping mass loading the next, until enormous volumes of sediment are in motion. The earthquake, in this sense, is not the cause of the disaster. The earthquake is the match. The unstable slope, with all its accumulated potential energy, is the gunpowder. This is the second mechanism, beyond tsunami earthquakes, that the warning system in 2026 was almost certainly responding to. Because submarine landslides do not require tsunami earthquakes to trigger them. They can be triggered by earthquakes of all sizes, sometimes even by earthquakes well below the threshold at which a fault rupture alone would generate a meaningful tsunami. The threshold for slope failure, in a place where the slope is already on the edge, can be quite low, and a magnitude 5.4 in the right place in the right geometry, with the right amount of shaking transferred to the right vulnerable layer, is not necessarily too small. I want to be careful not to oversell this. Most magnitude 5.4 earthquakes do not trigger catastrophic submarine landslides. The vast majority of them do nothing more interesting than a brief local episode of seismic shaking. The slopes do not fail, the sediment stays where it is, the ocean does not stir, but the operative word is most, not all. And in a corridor where the historical record includes a probable 200 cubic kilometre slope failure, the warning system cannot afford to assume that the next small earthquake will not be the trigger that releases the next big slide. The physics of submarine landslide tsunamis is in some ways even more troubling than the physics of fault rupture tsunamis. When a fault ruptures and displaces the seafloor, the displacement is, generally speaking, broad and shallow. The water above the fault is shoved up or down across a wide area, and the resulting wave has a long wavelength and a relatively modest amplitude. When a landslide displaces the seafloor, by contrast, the displacement is concentrated. The slide pushes water aside as it moves, and the wave generated by this lateral and downward shoving can have a much shorter wavelength and a much higher amplitude near the source. Landslide tsunamis are often, locally, much taller than fault rupture tsunamis. They do not propagate across ocean basins as efficiently as the long wavelength waves from megathrust ruptures, but in the immediate vicinity of the slide they can be devastating. Scotch Cap in 1946 was almost certainly hit by a wave that included a substantial landslide tsunami component. The 42-metre run-up is essentially impossible to explain through fault rupture displacement alone, especially at that distance from the epicentre. A submarine landslide on the slope just south of Unimak, releasing 200 cubic kilometres of material into the ocean, would have produced exactly the kind of locally enormous wave that the lighthouse experienced. The wave that crossed the Pacific to Hilo, by contrast, was probably more of a hybrid event, with the long wavelength fault component dominating at distance and the landslide component contributing additional energy at intermediate scales. The implication, when you connect this back to the central question of the 2026 alert, is that the warning system has to consider not just the earthquake itself, but also the possibility that the earthquake will trigger something much worse. A small earthquake that does not directly produce a meaningful tsunami can still, in this corridor, produce a meaningful tsunami indirectly, by destabilizing a slope that was already on the verge of failing. The probability of this happening in any given small earthquake is low, but the probability is not zero, and in a region where the consequences of the rare event are catastrophic, low probability is not the same as negligible. This is the non-linear hazard amplification that makes the Eastern Aleutians so unsettling. In a normal subduction zone, the relationship between input and output is roughly proportional. Bigger inputs produce bigger outputs in a more or less predictable way. In a slope failure-prone subduction zone, the relationship can become highly nonlinear. Small inputs can sometimes produce enormous outputs, depending on whether they happen to push the system past a critical threshold. The system has memory. The system has stored energy. The system can release that stored energy in pulses that bear no obvious relationship to the size of the trigger that set them off. I want to emphasize what this means in practical terms. There is no current technology that allows real-time monitoring of submarine slope stability across the eastern Aleutian margin. We do not have sensors on the slope itself that can detect in advance whether failure is imminent. We do not have seismometers that can distinguish, in the seconds after an earthquake, whether the earthquake has triggered a landslide. The first hint of a landslide-generated tsunami often comes from the tide gauges after the wave has already arrived somewhere. By that time, decisions about whether to warn are already in the past, so the warning system in 2026 was reacting not just to the possibility that the magnitude 5.4 was a tsunami earthquake in disguise, it was also reacting to the possibility that the magnitude 5.4 had triggered, or might trigger, a landslide that the seismometers would not see directly, but whose wave the system would have to anticipate through inference. The algorithm was, in effect, gambling on the worst case, and gambling on the worst case is, in this corridor, exactly what 80 years of accumulated experience has taught us to do. Part 6. Why this specific place? It is reasonable at this point to ask why all of this is concentrated in this one stretch of seafloor. The Pacific is a huge ocean, ringed by subduction zones, dotted with accretionary prisms and continental slopes and faults of every imaginable variety. Why does the Eastern Aleutian corridor in particular keep producing these anomalies? Why does this segment, more than its neighbours, behave in the unsettling, rule-breaking way that we have been describing? The answer is a combination of several factors that, individually, exist in many subduction zones, but whose particular combination here produces something unusual. The first factor is the geometry of the subducting slab. As I mentioned earlier, the Pacific Plate dives beneath North America at this point at a relatively shallow angle, around 10 degrees. Compare this to the subduction zones off Japan, where the slab descends at angles closer to 20 or 30 degrees in some segments. A shallower slab means a wider zone of contact between the two plates near the surface. It means that ruptures, when they happen, can extend further up dip into the shallowest and most poorly consolidated parts of the system. The second factor is the sediment supply. Alaska, over the past several million years, has been a giant glacial grinding machine. Ice sheets have repeatedly advanced and retreated across the southern part of the continent, pulverizing rock and dumping the resulting sediment into the rivers, which in turn delivered it to the coast and to the deep ocean. The Aleutian Trench, particularly in its eastern segments, has accumulated enormous volumes of this glacial sediment over time. The accretionary prism here is among the thickest anywhere in the world. There is simply more loose, water-saturated material draped over the fault here than there is over most other subduction zones. The third factor is the water content and pore pressure regime in the sediment. The accumulated sediment is not just thick, it is also, in many places, abnormally saturated, with pore pressures that may approach the lithostatic pressure of the overlying rock. High pore pressure reduces the effective stress on the fault and on the slope, which has two important effects. First, it makes the fault interface itself weaker, which favours slow, dispersed rupture rather than violent, high-frequency rupture. This is the regime in which tsunami earthquakes form. Second, it makes the slope itself less stable, lowering the threshold of shaking required to trigger landslides. Both of the mechanisms we've been discussing, slow rupture and slope failure, are encouraged by the same underlying condition. The fourth factor is the curvature and geometry of the upper plate. The eastern Aleutian corridor sits at a kind of bend in the arc, where the orientation of the trench and the direction of plate motion produce stresses that are not perfectly aligned. This can produce structural complications in the upper plate that further weaken the system. There are faults within the prism, splay faults rising off the megathrust, that may themselves be capable of significant slip. The whole architecture of the upper plate in this segment is more complex than in some other parts of the arc, and complexity in geology often translates to unpredictability in behaviour. You add all of this up and you get a fault segment that is, in a sense, optimised for the production of tsunamis from earthquakes that look modest. Slow rupture is favoured by the geometry and the pore pressure. Landslide triggering is favoured by the slope and the saturation. The shaking on land is suppressed by the same factors that enhance the displacement of the seafloor. Every aspect of the local geology pushes the system toward the same anomalous outcome. The corridor is not unusual because of any one factor. It is unusual because of the way these factors combine. This is the place that the 2026 warning system was watching when it fired the alert. This is the corridor whose history is encoded in the algorithm. And this is the geological complex whose behaviour we still, 80 years after Hilo, do not fully understand. There are open questions about the recurrence interval of large events here. There are open questions about whether the prism is failing continuously through small slumps or accumulating energy for catastrophic releases. There are open questions about how much of the historical record we can trust, given the limitations of older instruments and the difficulty of reading the seafloor for evidence of past slope failures. What we know for certain is that the corridor has done it before. What we suspect is that the corridor can do it again. And what we cannot know in advance is whether any given small earthquake is the harmless background noise of a fault grinding away or the trigger that releases the next big disaster. The system has to assume the second possibility, because the cost of being wrong about the first is so much smaller than the cost of being wrong about the second. Part 7. The detection problem. Even with everything we have learned in the past 80 years, there is a fundamental detection problem at the heart of all of this. Seismometers, the primary instruments by which we know that earthquakes are happening, are designed to detect the rapid motion of solid rock. They are not particularly good at detecting the slow motion of sediment, the gradual deformation of slopes, or the displacement of water. They are sensitive instruments, but they are sensitive to a specific kind of signal, and that signal is not always the signal that matters most for tsunami generation. A submarine landslide produces a seismic signal, but it is a different kind of signal from a fault rupture. It tends to be lower frequency, more dispersed in time, and harder to localize. In a busy seismic environment, with regional tectonic noise and distant earthquakes happening continuously, the signal of a landslide can be lost in the background. By the time analysts review the records and identify a probable mass movement, hours or days may have passed. This is not useful for real-time tsunami warning. The same is true to some extent for tsunami earthquakes themselves. The slow rupture characteristic of these events produces a seismic signature that is, by design, deficient in the high-frequency energy that traditional warning algorithms look for. Modern systems have been augmented with techniques that examine the long-period component of the spectrum, and these techniques have improved over the years, but they still operate under the constraint of the short window available before a near-field tsunami arrives. There is not always time to do the full analysis. Ocean buoys, particularly the deep ocean dart system, are the gold standard for confirming that a tsunami is propagating. They sit on the seafloor, in deep water, and measure the pressure of the water above them. When a tsunami passes, the pressure changes by a small but detectable amount, and the buoy reports this back to the warning centre. The buoys are remarkable instruments. They can detect tsunami waves that are only a few centimetres tall in the open ocean, but they only give you data after the wave has passed them. If the tsunami is generated near the coast, the wave may already be on the shore by the time the nearest buoy reports anything. The buoys are essential for confirming far-field events. They are limited for confirming near-field ones. Tide gauges along the coast give you information even later. By the time a tide gauge records a wave, the wave has, by definition, already reached the coastline. For people standing on the beach, the tide gauge confirmation is too late to be useful. The tide gauges are good for understanding what happened. They are not particularly good for warning that something is happening. This is the technological landscape in which the warning system in 2026 was operating. The system had seismometer data. It had estimates of magnitude, depth, and location. It had whatever long-period analysis its algorithms could complete in the first few minutes. It did not yet have buoy confirmation. It did not yet have tide gauge data. It had to make a decision under fundamental uncertainty, with imperfect information, knowing that the cost of waiting for better information was potentially catastrophic. The decision the system made was to warn, and it made that decision in 3 minutes. There are technologies on the horizon that may, in time, reduce the uncertainty inherent in this kind of decision. Real-time seafloor monitoring systems, where pressure sensors and accelerometers are deployed directly along the slope and connected to shore by fibre optic cable, are being developed and tested in some parts of the world. Japan, after the 2011 Tohoku event, has invested heavily in such systems, deploying networks of seafloor instruments along its eastern margin that can detect ruptures and tsunamis in their immediate vicinity. The United States has begun similar investments along parts of the Cascadia subduction zone, but the eastern Aleutian corridor remains, by and large, instrumented at a much lower density. The cost and logistical difficulty of deploying and maintaining seafloor instruments in the open North Pacific are substantial. The corridor remains, for now, a place where decisions have to be made on inferred risk rather than measured signals. This means that, for the foreseeable future, the warning system will continue to operate in much the way it operated in 2026. It will continue to fire on small earthquakes in this corridor that would not trigger alerts elsewhere. It will continue to issue precautionary warnings that, most of the time, will be downgraded after the fact when no tsunami appears. It will continue to live with the trade-off between alert fatigue and missed disaster, leaning as it has since 1946 toward the former rather than the latter, and it will continue to remember. Part 8. The Tsunami Gap. Just to the east of the corridor where the 2026 earthquake happened, sits a stretch of fault that has its own set of unsettling properties, although they are different from the ones we've been discussing. This stretch is called the Tsunami Gap, and it has been quietly puzzling seismologists for the better part of a century. A seismic gap, in the language of fault studies, is a stretch of an active plate boundary that has not produced a major earthquake in the historical record, even though the surrounding stretches have. The idea is that if a fault is locked, accumulating stress through plate motion, then eventually that stress has to be released. If a long stretch has gone unusually long without a major rupture, it might be storing up energy for a future event, or it might be doing something else entirely, slipping silently or creeping in a way that does not produce earthquakes. The gap might be a quiet, patient threat, or it might be benign. It is genuinely difficult in many cases to tell which. The Tsunami Gap is a stretch of the eastern Aleutian megathrust between two segments that have produced major earthquakes within the past century. To the west, there have been events in the 20th century. To the east also. But the Tsunami Gap itself, despite occupying a position along the same overall fault system, has not produced a comparable rupture in the modern record. There are some uncertain historical reports from the late 1700s that suggest a possible event in the area, but the evidence is fragmentary and the interpretations are contested. GPS measurements, which can detect the gradual movement of the upper plate as it is dragged along by the descending slab, have been used to estimate how locked the Tsunami segment is. The results have been ambiguous. Some studies suggest that the segment is partially locked, accumulating stress at a rate that, over time, would be capable of producing a major rupture. Other studies suggest that much of the segment may be creeping, slipping aseismically without storing up the kind of energy that would feed a catastrophic earthquake. The truth is probably somewhere in between, with different subsegments behaving differently, and with the locking pattern itself potentially evolving over time. There is also paleo-tsunami evidence, in the form of sand layers and other deposits found in coastal lakes and marshes around the Alaska Peninsula and surrounding areas, that suggests large tsunamis have hit this part of the coast at irregular intervals over the past several thousand years. Some of these deposits are difficult to attribute to a specific source. They could be from ruptures of the Tsunami Gap itself. They could be from neighbouring segments. They could be from far-field events that manage to propagate into local geometries and produce significant run-up. The geological record is suggestive but not conclusive. The relationship between the 2026 earthquake and the Tsunami Gap is geographic rather than mechanistic. The earthquake happened in the broader eastern Aleutian region, near but not directly within the gap itself. The fault rupture, whatever it was, did not directly involve the locked or partially locked sections that worry seismologists most. But the proximity is meaningful. Earthquakes that happen near a seismic gap can, in some cases, alter the stress state on the gap itself. They can transfer stress onto adjacent locked sections in ways that over time may bring those sections closer to or further from rupture. They can also serve as reminders that the broader fault system is active, that the plates continue to converge, and that the energy budget of the region is not at rest. The 2026 warning system, when it fired its alert, was reacting to the immediate event, not to the Tsunami Gap. But the gap is part of the broader context that makes the eastern Aleutian corridor such a sensitive region. It is one more piece of evidence that this stretch of seafloor harbours significant hazard that is not yet fully understood. The warning system does not know what the Tsunami Gap will do next, neither does anyone else. And that uncertainty, layered on top of all the other uncertainties we have been discussing, contributes to the precautionary doctrine that governs the system's decisions. I want to keep this section grounded in our central thread because the gap is interesting, but it is not what triggered the alert. The alert was triggered by a small earthquake near a fault segment with a known capacity to produce wildly disproportionate tsunamis through some combination of slow rupture and submarine slope failure. The Tsunami Gap is a separate hazard, geographically nearby but mechanistically distinct, and its presence is part of why the entire region is treated with such care by hazard scientists. But it is the corridor itself, with its history of 1946 and its peculiar geology, that fired the alert, not the gap. The gap is just one more reason not to take any earthquake in this part of the world lightly. Part 9. The false signals problem. There is an aspect of all of this that I have only touched on so far, but that I want to spend some time on now because it shapes the experience of living with a warning system that operates on the precautionary doctrine. That aspect is the problem of false signals. In any given year, the Eastern Aleutian Arc produces dozens of magnitude 5+ earthquakes. The vast majority of them do not produce tsunamis. The vast majority of them do not even come close to producing tsunamis. They are routine background activity for an active subduction zone. If you are someone who follows earthquake monitoring closely, you can watch them tick by on the various agency websites one after another, week after week. The fault is alive. The fault is grinding. None of it, almost ever, becomes a disaster. But because of the historical record, because of 1946, because of the capacity of this corridor to occasionally produce events whose tsunami consequences far exceed their seismic signature, the warning system has to treat each of these earthquakes with greater suspicion than it would treat similar events elsewhere. Most of those magnitude 5s do not trigger alerts, because most of them happen in parts of the arc, or at depths, where even the most cautious algorithm decides the risk is acceptable. But occasionally, when the location is close enough to the dangerous corridor and the depth is shallow enough, the system fires, and then the alert resolves with no observable wave. The buoys stay quiet, the tide gauges stay flat, and the system gets criticised in some quarters for crying wolf. This is the false signals problem, and it is a fundamental tension at the heart of every warning system in the world. A perfectly tuned system, one that fired only when a real disaster was on the way, would be ideal. But such a system is impossible to build because the information needed to make the decision with perfect accuracy is not available within the window of time during which the warning needs to go out. Every system has to make probabilistic decisions on partial data. Every system will sometimes warn when no disaster comes, and every system will sometimes miss events that turn out to be disasters. The question is not whether a system can be perfect. It cannot. The question is how the system trades off between false alarms and missed disasters. A system that minimizes false alarms will, almost by definition, occasionally miss real events, because to minimize false alarms you have to set higher thresholds, and higher thresholds will let some real events slip through. A system that minimizes missed disasters will, almost by definition, produce more false alarms, because to catch every real event you have to set lower thresholds, and lower thresholds will sometimes fire on noise. The Pacific Tsunami Warning Center and the broader tsunami warning infrastructure of the United States has historically chosen to bias toward the second strategy. More false alarms, fewer missed disasters. The reasoning is that the cost of a false alarm, while real, is bounded. A few hours of disruption, some economic loss, some erosion of public trust. The cost of a missed disaster is by contrast potentially unbounded. It can be measured in human lives. It can change the geography of a coastline. It can leave scars that last for generations. When the system fired in 2026 on a magnitude 5.4, it was operating squarely within this bias. The system was designed to fire on this kind of event in this kind of place, even at the cost of producing alerts that would later look unnecessary. The institutional designers of the system knew, when they set the thresholds, that they were committing to a future of occasional false alarms. They made that commitment with their eyes open, because the alternative was to risk repeating 1946. I think this is worth pausing on, because the public perception of warning systems often treats false alarms as failures. They are not failures. They are the visible, irritating side of a system that is, in its quieter moments, actively saving lives by treating seriously the ambiguous signals that, if ignored, could occasionally turn into disasters. The fact that you see the false alarms and not the disasters that did not happen is exactly what success looks like in this domain. It is the opposite of failure. It is failure in visibility. The system catches the rare true events by being willing to fire on the much more common borderline ones. If you only saw the system fire on real disasters, it would be because the system was missing most of the real disasters too. This is hard to internalize. It is counterintuitive. It feels, to the untrained eye, like the system is broken because it keeps issuing alerts that do not pan out. But the alternative, a system that issues alerts only when it is sure, is a system that, in a place like the Eastern Aleutian Corridor, would have missed the conditions that produced the 1946 event entirely. Because the seismic data of 1946 did not, by itself, look like a Pacific Basin disaster. It looked like a moderate event. The system that would have missed 1946 is the system that minimizes false alarms. The system that catches the next 1946 is the system that lives with them. So when the algorithm fired in 2026 on a magnitude 5.4 and the alert was downgraded a few hours later with no observable wave, what happened was not a malfunction. What happened was a system performing exactly as designed, in a corridor that has earned the precaution, on a fault segment that retains the capacity to surprise us. The wave did not come this time. That does not mean the system was wrong. It means the wave did not come this time. The next time the algorithm fires, in this place, the question of whether the wave will come will be just as open as it was today, and the system will fire again, because that is what 80 years of accumulated experience has taught it to do. Part 10. The North Pacific Context. Let me briefly address something that has been part of the broader news coverage around the 2026 event, but that I do not want to overweight. The North Pacific, in the period leading up to this earthquake, has been seismically active. There have been swarms of magnitude 5 and above events along the Kamchatka Peninsula on the Russian side of the arc. There has been heightened activity at Shisheldine volcano in the Aleutians, with gas emissions and minor explosions. Great Sitkin volcano, also in the Aleutians, has been intermittently restless. The arc as a whole has been, by recent standards, more lively than usual. It is tempting, when you look at all of this, to draw connections, to see the Aleutian earthquake as part of a broader pattern of activation, perhaps even to suggest that the Pacific Rim is somehow gearing up for something larger. I want to be careful here, because the temptation does not match the evidence. There is no established mechanism by which volcanic activity in one part of the arc would directly trigger seismic activity in a different segment thousands of kilometers away. Earthquake swarms in Kamchatka and the eastern Aleutian corridor are, for the most part, independent phenomena driven by local conditions, even though they share the broader context of the Pacific Plate descending around its edges. The 2026 warning when it fired did not fire because of anything happening in Kamchatka or at Shishaldin. It fired because of what happened at one specific set of coordinates near Sandpoint, in a corridor whose local history demanded a precautionary response. The North Pacific context is interesting. It is worth noting. But it is not the cause of the alert. The cause of the alert is the local fault, the local sediment, the local memory of 1946. The broader regional activity is background, not driver. This is actually an important point about how we interpret hazard signals in general. There is a strong human tendency to look for connections, to see patterns, to assume that when many things are happening simultaneously, they must be related. Sometimes they are. Often they are not. The Pacific Rim is, by its nature, an active place. Earthquakes happen along its length continuously. Volcanoes erupt regularly. Tsunamis are generated, more often than the public realizes, somewhere along its margins. The simultaneous occurrence of activity in different regions is, much of the time, simply what an active plate boundary system looks like in normal operation. The 2026 event was a local anomaly in a corridor with a specific history, evaluated by an algorithm with a specific memory of that history. Treating it as part of a global pattern misses what makes it interesting. What makes it interesting is precisely how local it is, how specific, how tied to a particular accretionary prism, a particular slab geometry, a particular ghost of a wave from 80 years ago. The system did not fire because the Pacific is angry. The system fired because this exact piece of the Pacific, with this exact history, is treated by the warning algorithm as a place where small earthquakes deserve big responses. And that decision was made long before 2026 by people working from the lessons of 1946. Part 11. The Solar and Geomagnetic Dead End. There is one more piece of context I want to address before moving into the deeper analysis, and that is the question of solar activity. In recent years, there has been increasing public interest in the possible relationship between space weather and earthquakes. Some commentators have suggested that solar flares, geomagnetic storms, or other space weather phenomena might somehow trigger seismic events on Earth. When a notable earthquake happens in a period of active solar conditions, these proposed connections sometimes get amplified. I want to be straightforward about this. The evidence for any direct causal link between solar activity and earthquakes is, at best, extremely weak. There is no established physical mechanism by which a solar flare or a coronal mass ejection would significantly alter the stress state on a fault deep in the Earth's crust. The energies involved in plate tectonics dwarf the energies that solar activity deposits into the upper atmosphere. The two systems operate on essentially independent scales, with no plausible pathway for one to drive the other. In the case of the 2026 earthquake, the geomagnetic conditions at the time of the event were quiet. There was no major geomagnetic storm. There was no significant solar flare in the immediate run-up to the rupture. Even if you wanted to argue for a solar trigger, the basic timing does not work. The solar question is, for this event, a dead end. The corridor produced a small earthquake because the corridor was going to produce a small earthquake, driven by the slow grinding of the Pacific Plate beneath North America, which has nothing to do with what the sun was doing on any particular morning. I bring this up not to dwell on it, but to clear it from the table, because I think it is important that when we are trying to understand a complex hazard event, we focus on the mechanisms that actually drive it. The drivers here are tectonic. They are local. They are encoded in 80 years of Pacific Tsunami Warning Center experience and in millions of years of slab descent and sediment accumulation. The sun is not part of the picture. The corridor is. So with that out of the way, let us turn to the question of what the 2026 event actually means in the context of everything we have just covered. Was this a foreshock of something larger? Was the warning correct? What is the actual risk going forward? And how should we think about events like this when they happen, as they will continue to happen in this remarkable and dangerous stretch of seafloor? Part 12. Not a foreshock. There is a question that always gets asked, in the wake of any moderate earthquake in a known hazard zone, and the question is whether the earthquake might be a foreshock for a larger event yet to come. The question is reasonable, it comes from a real place. People want to know whether the small tremor they just experienced is a warning of something worse on the way. And in the 2026 case, with the alert and the historical context and all of the surrounding noise, the question has been asked more loudly than usual. The honest answer, supported by decades of statistical research on earthquake sequences, is that almost certainly not. The vast majority of magnitude 5.4 earthquakes are not foreshocks. They are isolated events, or aftershocks of earlier ruptures, or routine background activity in active fault zones. They come, they go, they leave behind a small adjustment in the local stress state, and life on the fault continues much as before. The probability that any given magnitude 5 earthquake in an active subduction zone is the prelude to a much larger event in the near future is low. Not zero, but low. The way seismologists think about this is in terms of conditional probabilities. Given that an earthquake of a certain size has occurred in a certain region, what is the probability that a larger earthquake will occur in the same region within some specified time window? The answer depends on the region, the size of the initial event, and the time window in question, but generally speaking the probability is small, on the order of a few % or less for the kind of dramatic escalations that the foreshock question implies. This does not mean foreshocks do not happen, they do. There are notable historical cases, including some events along subduction zones, where moderate earthquakes preceded much larger ruptures by hours or days. But these cases are rare, and crucially, they are usually only identifiable as foreshocks in retrospect. There is no reliable way to look at a magnitude 5.4 in real time and determine whether it is going to be followed by a magnitude 8 in the next few hours. The statistical signature of foreshocks is too weak, and the false alarm rate too high for any useful predictive system to be built on this basis. So no, the 2026 earthquake should not be interpreted as a foreshock. The default assumption, until evidence emerges to the contrary, is that it was an isolated event, a single small rupture in a long history of small ruptures along an active plate boundary. The warning system did not fire because the algorithm thought a foreshock was in progress. The warning system fired because the event itself, on its own merits, in this specific corridor, deserved a precautionary response. Those are two different things, and conflating them muddies what the alert was actually about. The deeper point here is that our culture has a kind of narrative hunger when it comes to natural disasters. We want events to mean something. We want small tremors to be omens of larger ones. We want the world to be telling us a story with foreshadowing and rising action and climactic moments. And the world, in its tectonic operations, is mostly not doing this. It is grinding along according to its own indifferent physics, producing earthquakes and tsunamis when the local conditions favour them, and not according to a narrative arc that humans can follow. Sometimes a small earthquake is just a small earthquake. The story we want to read into it is our own. This does not mean the 2026 event was meaningless. It means the meaning of the event lies elsewhere. The event matters because of what it tells us about the warning system, about the corridor, about the science that we still do not fully understand. It does not matter, probably, as a predictor of the next big rupture. The next big rupture will come when it comes. It will not be heralded in any reliable way by a magnitude 5.43 months in advance. We will not get a clean warning. The warning we get will be, in all likelihood, the rupture itself, and the system will have minutes at most to translate that rupture into action. Part 13. Why the warning was correct. Despite the fact that no tsunami arrived, despite the fact that the alert was downgraded within hours, despite the fact that to many casual observers, the whole episode might look like the system overreacting, I want to argue that the warning was correct, not just defensible, correct. The right decision, made on the right information, by a system that has been carefully designed to make exactly this kind of decision in exactly these kinds of circumstances. The framework for evaluating warning decisions cannot be retrospective. You cannot look at what happened after the fact and judge the decision based on the outcome. That would be like judging a doctor's decision to order a biopsy based on whether the biopsy came back positive. If the biopsy comes back negative, that does not mean the doctor was wrong to order it. It means the doctor was operating on a real probability, and the probability resolved on the lower side. The decision was correct given the information available at the time, even though the outcome was, in this case, not a confirmation. The same logic applies to the 2026 warning. At the moment the alert was issued, the algorithm had access to the location, depth, and approximate magnitude of an earthquake in a corridor with a specific and well-documented capacity to produce disproportionate tsunamis. The algorithm did not have access to confirmation from ocean buoys or tide gauges, because those instruments had not yet had time to detect anything. The algorithm had to make a probabilistic judgment about whether a tsunami was likely enough to warrant warning, and the answer, given the corridor and the historical record, was yes. The fact that no tsunami appeared does not retroactively make the warning wrong. It means the probability that the algorithm had calculated, the elevated probability that a tsunami might be coming, did not resolve in this case as a confirmed wave. Most of the time, when this kind of warning is issued, the wave will not appear, because most of the time, even in this corridor, small earthquakes do not produce significant tsunamis. The system knows this. The system is not surprised that the wave did not appear. The system is willing to accept many such non-confirmations in exchange for the rare cases when the wave does appear and the warning saves lives. This is the nature of operating under uncertainty in a domain where the consequences of error are highly asymmetric. False alarms cost something. They cost time, attention, public trust. But they do not cost lives, except indirectly through the slow erosion of credibility over many years. Missed alarms, by contrast, can cost lives directly and catastrophically. A single missed event, if it produces a wave on the scale of 1946, can kill more people than a decade of false alarms could possibly demoralize. The math is not close. The bias toward warning, in the Eastern Aleutian Corridor, is the only rational position given the asymmetry. I want to take a moment to acknowledge what this means for the people who actually have to respond to the alerts. For coastal residents along southern Alaska, for emergency managers who have to coordinate evacuations, for radio stations and broadcasters and digital systems that have to relay the warnings, every alert has a real cost. People wake up in the middle of the night. People drive to higher ground. Businesses close. Schools delay. The disruption is genuine, and the people experiencing it are not wrong to feel it. They are also not wrong, in the moments after a downgrade, to feel a certain weariness, a sense that the system has cried wolf again. But the wolf, in this corridor, is real. It has visited before. It will, on some schedule that none of us can predict, visit again. And the only way to be ready, given the limitations of our science and our instruments, is to live with the cries. The wolf cries that turn out to be nothing are the price we pay for the ones that turn out to be everything. There is no other way to do this. There is no system anywhere on Earth that has solved the problem of perfect tsunami warning. The systems that exist are doing the best that current science and engineering allow, and they are doing it in places like the Eastern Aleutian Arc, with a built-in respect for what the past has taught. The warning in 2026 was correct. The warning would be correct again if the same thing happened tomorrow, even though the result would, in all probability, again be a downgrade with no observable wave. The warning will continue to be correct every time the algorithm fires in this corridor, until and unless the science improves to the point where we can reliably distinguish dangerous events from benign ones in real time. And we are not currently anywhere close to that point. The corridor will continue to surprise us. The system will continue to react to those surprises with the only rational response available, which is precaution. Part 14. The real risk is not the earthquake. I want to circle back to something I touched on earlier and develop it more fully, because I think it is the single most important takeaway from this entire story. The real risk in the Eastern Aleutian Corridor is not the earthquake itself. It is what the earthquake might unleash. When most people think about earthquake hazard, they think about the shaking. They think about buildings collapsing, ground rupturing, people being injured by falling objects. That is the standard mental model, and for most regions of the world it is the right one. The shaking is what kills you in an earthquake. The shaking is what destroys infrastructure. The shaking is the primary signal that something dangerous is happening. In the Eastern Aleutian Corridor, this mental model breaks down. The shaking is, often, the least dangerous thing about an earthquake here. The population density is low. There are no large cities directly atop the fault. The buildings that exist are, by and large, modest structures designed to withstand at least some seismic loading. A magnitude 5.4, or even a magnitude 6 or 7 in this region, is unlikely to cause catastrophic on-land damage simply because there is not that much on land to damage. What can be catastrophic, though, is what happens to the water. Whether through slow rupture that displaces the seafloor in ways the seismic record does not fully capture, or through submarine landslides triggered by the shaking, or through some combination of both, the corridor is capable of producing waves that travel across the entire Pacific basin and kill people thousands of kilometers away. The ocean is the medium through which the earthquake's danger is delivered to populated coastlines. The ocean is not a passive bystander, the ocean is the weapon. This is the framework I think people need to internalize when they hear about earthquakes in this region. The question is not, how big was the shaking? The question is, what did the shaking do to the water? And the answer to that second question is not, in general, derivable from the first. You can have a moderate earthquake that produces a massive wave, as in 1946. You can also have a fairly large earthquake that produces relatively modest waves if the geometry and the slope conditions happen not to favor amplification. The relationship is non-linear and, to a significant extent, unpredictable. This non-linearity is what makes the Eastern Aleutian Corridor genuinely scary. In a linear hazard system, you can plan for the worst case based on extrapolation from observed events. You watch for the largest possible earthquake, you model what wave it would produce, and you prepare for that. In a non-linear hazard system, the worst case can emerge from inputs that look unremarkable. You cannot reliably extrapolate. You cannot watch for the largest earthquake, because the largest tsunami may not come from the largest earthquake. It may come from a moderate earthquake that happens to land at the wrong place at the wrong time, when the slope is at its most precarious, when the sediment is at its most saturated, when the rupture happens to extend into the shallowest and weakest part of the fault. The implication for coastal populations is unsettling. It is not enough to know the magnitude of an earthquake to know whether you are at risk. The information that would actually tell you whether you are at risk, the detailed condition of the seafloor, the precise nature of the rupture, the immediate response of the slope, is information that is not available in the minutes and seconds when you would need it. You're operating in conditions of irreducible uncertainty. The warning system, doing its best, is also operating in those conditions. Everyone is. This is why, when an alert fires for a magnitude 5.4 in this corridor, the right response is to take it seriously, even if the alert is later downgraded. The fact that the wave does not come this time does not mean the wave cannot come next time. The fact that most magnitude 5.4s are routine does not mean that this magnitude 5.4 was routine, until enough time has passed and enough data has come in to confirm that it was. The default response in the face of uncertainty has to be the response that protects the most lives in the worst case. And the worst case here is bad enough that even unlikely scenarios deserve serious treatment. There is a broader point here about how we live with hazards in the modern world. We have built, over the past century, an enormous infrastructure of detection and warning that is supposed to insulate us from the worst consequences of natural events. The infrastructure works most of the time, but it works by absorbing uncertainty on our behalf and translating that uncertainty into actionable signals. The signals are not always accurate. They are sometimes too cautious, sometimes not cautious enough, but they are doing the work that, in earlier eras, was simply not done at all. The people of Hilo in 1946 did not have a system absorbing uncertainty for them. They had nothing. They had only the ocean. The people of southern Alaska in 2026 had 3 minutes. The people of any future Hilo, somewhere along a Pacific coastline, will have whatever the system is capable of giving them in the moments after the next big rupture. That is the bargain we have made. It is not a perfect bargain. The system will sometimes get it wrong in both directions, but it is the bargain that has emerged from 80 years of trying to do better than we did in 1946, and it is, in 2026, the best we have. Part 15. The Core Mystery. I want to end where I started, with the central mystery. Why this place? Why this corridor? Why does the Eastern Aleutian Arc, more than any other comparable stretch of subduction zone, produce events that surprise us? We have walked through the components of the answer. We have looked at the slab geometry, the sediment thickness, the pore pressure regime, the slope instability, the historical record. Each piece, by itself, contributes something. The combination is what produces the unsettling whole. But even with all of these pieces, there is still something we do not fully understand. We do not, for instance, know what triggers the major slope failures. We have hypotheses. We think large earthquakes can do it. We think possibly smaller earthquakes can do it under the right conditions. We think there may be other factors, such as long-term sediment accumulation reaching critical thresholds, or pore pressure fluctuations driven by tides or seasonal cycles, that can prime the slopes for failure. But we do not have a comprehensive model that lets us predict, with any confidence, when the next big slide will happen, or what magnitude of earthquake would be required to set it off. We do not know the true recurrence interval for events on the scale of 1946. We have one event in the historical record, plus some paleo-tsunami evidence that suggests other events have happened in the deeper past. But we do not have enough data to draw a confident frequency curve. Are these events something that happens every few hundred years? Every few thousand? Are they clustered in time, with multiple events occurring within a few centuries and then long quiet periods? We do not know. The geological record is too sparse, and the modern instrumental record is too short to resolve these questions. We do not fully understand the dynamics of the sediment itself. The accretionary prism south of Aleutian Island is a complex three-dimensional body of material with internal layering, internal weak surfaces, and internal pore pressure variations that are extremely difficult to characterize in detail. We have some seismic reflection profiles. We have some borehole data in places where research vessels have drilled into the sediment to retrieve cores. But our knowledge is patchy and incomplete. The detailed structure of the prism, in many places, is still inferred rather than measured. These unknowns are not just academic curiosities. They are practical limitations on our ability to predict and prepare for the next big event in this corridor. Every one of them represents a place where the science has not yet caught up to the hazard. Every one of them is a place where future research could meaningfully reduce uncertainty and improve warning systems. The Eastern Aleutian Corridor is, in this sense, a frontier, a piece of the planet whose behaviour is still being decoded, slowly and at considerable expense, by researchers who have to take to the open North Pacific in research vessels and deploy expensive equipment in punishing conditions to gather the data we need. I think there is something important about acknowledging this. We live in a time when it is easy to imagine that science has answered most of the questions that matter, that the natural world is largely understood, that the unknowns are confined to the cosmically distant or the impossibly small. The Eastern Aleutian Corridor is a reminder that this is not true. There are pieces of our own planet, well within reach of our instruments and our research vessels, where major hazards operate according to mechanisms that we still do not fully grasp. The next 1946 is going to come, eventually, from somewhere in this corridor or one like it. We do not know exactly where. We do not know exactly when. We do not know exactly how big it will be. We do not know exactly what mix of fault rupture and slope failure will produce it, and we are working as fast as our funding and our instruments and our intellectual frameworks allow to fill in those gaps before the next event arrives. In the meantime, the warning system stands watch. It absorbs the uncertainty on our behalf. It fires when the corridor twitches in 3 minutes or less, even when the twitches are small. It accepts the false alarms because the alternative is unacceptable. It carries the memory of 1946 like a digital ghost, encoded in thresholds and decision rules, ready to scream the moment the patterns it has learned to fear appear again on its screens. The 2026 earthquake did not change the system. The system was already what it is. What the 2026 earthquake did was remind us that the system is doing something, that it is not a piece of background infrastructure that runs quietly in the corner of an emergency operations centre. It is an active sentinel watching a corridor that has earned its watchfulness, ready to act on partial information when the cost of waiting is too high. The corridor is still there, the fault is still there. The sediment is still piled on the slope, water saturated and gravitationally precarious, sitting on a slab that is still descending at 6 to 7 centimetres per year. The plates are not negotiating with us. They will continue what they have been doing for millions of years, and at some point, with no reliable warning, they will produce another event. It might be tomorrow, it might be a century from now, It might be tomorrow and again a century from now and again 1,000 years after that. We do not know. We cannot know. We can only watch. And so we watch. Today's earthquake was a magnitude 5.4. The warning fired in 3 minutes. The wave did not come. The alert was downgraded. Life along the southern Alaskan coast resumed. The ocean returned to its quiet, indifferent rhythm. Tomorrow there will be another small earthquake somewhere along the Aleutian Arc, and probably it will not produce an alert, and probably it will not produce a wave. And the day after that, and the day after that. The watching continues. But somewhere, in the silicon memory of the warning system, the coordinates of 1946 are still flagged. The corridor is still treated as special. The thresholds are still tilted toward precaution. And when the next event comes, whether it is a small one that fires the algorithm and resolves quietly, or a large one that justifies every decision the system has ever made, the response will be the same. 3 minutes. The alert. The chance, however slim, to do better than 1946 did. Today's earthquake didn't change the system. It reminded us that we still don't understand it. And in a corridor that has been quietly rewriting the rules of tsunami science for almost a century, that reminder might be the most important thing the magnitude 5.4 ever does. The fault will go back to grinding, the sediment will go back to settling, the warning system will go back to watching, and the rest of us, the people who live with the bargain that 80 years of disaster and recovery and engineering have produced, will go back to whatever we were doing before the alert flashed across our screens. The ocean, of course, will keep its own counsel. It has always kept its own counsel. It does not tell us in advance when it is going to rise. It tells us, when it tells us at all, by rising. And the only thing standing between that rising and the people who would otherwise be taken by it is a system that fires in 3 minutes, on partial information, in a corridor that has earned every gram of caution we have ever extended to it. The system fired today, the system was right to fire, and somewhere out there beneath the cold grey water south of Unimak Island, a slope of saturated sediment is sitting on the edge of failure, waiting, the way it has always been waiting, for a trigger we will not see coming until it has already arrived. That is the corridor. That is the bargain. That is the story today's magnitude 5.4 was actually telling us if we were willing to listen. And we should be, because the next time the ground moves at these coordinates, the wave that does or does not follow will not care whether we were paying attention. It will only care whether we were ready. And ready, in this corridor, has always meant the same thing. 3 minutes, the alert, the memory of 1946 sitting in the code waiting to fire one more time.